So, good morning, everyone. My name is José Pellicer, and I'm from the University of Valencia, and I'm going to be presenting the research that I've been doing as a postdoc over the last year and a half or so. Maybe some of you may know me from ValgrAI because I presented my PhD thesis, and I got the first prize for it. And that was in prostate lesion detection with image analysis and AI, but this has nothing to do with it. So this is like what I've been working on over the last year or so. So the topic of this talk is going to be explainable AI and AI for Earth surface forecasting. So this has to do with the use of satellite data for the detection of extreme events and the prediction of future satellite reflectances. So what we're, maybe 1 second. Yeah, so here we can see one example of how this data looks like. So this is an image from a series of images from Sentinel-2, which is a satellite from the ESA, which funded this project. And it is captured one image every 5 days. And the purpose of the AI model that I'm going to train is to predict basically the next time step, so the reflectances at the next time step. And we also have some additional input variables, as I will describe. And we can see that the data set encompasses the whole Earth, and it is focused on the detection of extreme events, so it is not sampled uniformly, but it is sampled in the regions that are more, where there are more extreme events. And when I'm talking about extreme events, I'm talking about heat waves, and I'm talking about droughts. And yeah, also to know that when you're training with this kind of data, you have to do both time and correlation for the test set. So you train with data until 2021, and then you test on 2022, for instance, and it also has to be geographically uncorrelated by taking like let's say, a border around your test data that it's at least 50 kilometers away from the training and validation data. Also including, other than the satellite data, we are also including a cloud mask. And we are also including some vegetation land cover, which just tells us the kind of vegetation that there is in this image. And we are also including weather variables, such as surface pressure, air temperature, etc., because these do help in the prediction. The model is a 3-layer convolutional LSTM that basically takes all the past context and predicts the next time step. It does so by only predicting the anomalies or the difference with respect to the climatology. And this is interesting because it has a lot of nice advantages for the network. And we're training with an L1 or mean absolute error loss, and we are computing also in the loss the KNDVI, which is a measure for vegetation greenness, and it allows us to evaluate impacts. So training the network and propagating the loss directly through this equation leads to better results when we are going to use this metric. Here are some of the results. I will just highlight maybe the results in the test set here, which is an R2 of about 0.9, and it also works well when there are extreme events happening. And these are like some baselines to compare against, so it is significantly better. On the top 3 rows, we would see what the actual reflectances for the RGB bands of the satellite look like, then for the infrared, and this would be the KNDVI, which is an index on top of these values. And here we would see the predictions, and remember this is 1 time step ahead. But still, you can see that even when it is completely cloud covered, it is able to predict the fall of the snow. And it also is able to predict, which is also interesting, the progressive greening of the vegetation after some precipitation, etc. And the interesting part, or like one of the main purposes of this project, was to be able to predict and analyze the drivers for extreme events. And in particular, we focused on this one, on the October 2020 Central South America heat wave, which was huge in terms of time duration, in terms of impacts. The record temperatures were recorded. There was a lot of affectation to the vegetation there. It was large in extension, many South American countries. And what we're doing here is sort of, so we're using explainable AI to analyze what are the drivers, so how the neural network actually what is it using in order to predict when the vegetation impacts, when there is this event happening and when not. And what we see is that some measures, such as the climatologies, have a very great impact when there is no event happening, so in the normal conditions, and they have a very small impact when there is an event happening. And then it is actually anomalies like the minimum evaporation, the minimum surface latent heat flux that have a strong impact when the event is happening, which actually makes sense. And I could go on for a bit longer, but I have to stop. So just as a summary, we have proposed this model for AI and explainable AI that can help us predict and also understand the drivers of extreme events such as heat waves and droughts. And well, we use some sort of modeling techniques and explainable AI in order to do this research, which are novel to this field, because yeah, it is high-dimensional data and it's complex to work with, and yeah, we achieved these results. So yeah, thank you, everyone.